In this follow-up class on determinants, we're going to look at a few other properties which are important both for mostly for a historical point of view and partly from a technical point of view, although we are going to work with determinants in a way that is going to use these properties very marginally. Still, there are properties that you need to know about. In particular, we're going to have a quick look at two traditional methods. One is called the Laplace expansion theorem, and this is actually a theorem that in many textbooks is used as actually the definition of a determinant. Once I show you what the method is like, you'll understand, I hope, why I prefer to give you the other definition of determinants, because this method here is fairly lengthy. It does have one advantage, and I'll show you what it is once we get there. The other method that we're going to look at is Cramer's rule. And again, this is a traditionally very famous method for solving certain types of linear systems. The reason why I'm not going to emphasize it very much is the fact that, again, it's not particularly efficient from the computational point of view, and contrary to what we're trying always to do in linear algebra, is not easily generalizable. It's a rule, it's there, and you can use it if you need to. So these methods, what they have in common is the fact that both of them have historical significance. They're traditional methods, so you want to know something about them because probably other people have heard about them, and you will run into them at some point or the other. The other one is that unfortunately they're longer and more boring or complex than the methods that we will actually be using in class. So from one point of view, this class, you may wonder, why do we have to go through that? But yes, we do. On the other hand, just look at the bright side. We're not going to focus on these particular methods. And also keep in mind that they are useful in some situations. So there may be some situations where these two methods, although they may look a little bit cumbersome, but they may end up being quite effective in what they're planning to do. In order to explain what the Laplace expansion theorem says and how it works, I have to first of all introduce a couple of new jargon words which are related to that theorem. These words relate to concepts that can be applied in many situations, but we're pretty much going to see them all only in the context of this Laplace expansion theorem. The first one, of course, is this concept of a minor. What am I talking about? We're not talking about people who are underage and cannot drink legally, but what we're talking about is some part of a matrix. So given a matrix A, consider the smaller matrix Aij, and I know there is a problem with the notation there, but I'll tell you more about it in a second. So what we're going to do is we're going to construct a smaller matrix obtained by deleting the ith row and the jth column of this matrix A. Okay, so let's say we have a matrix that looks like this. Let's say that we want to construct the minor A2, 3. What that means is that what I'm going to do is I'm going to delete the second row and the third column from that matrix. And what I'm left with, I'm going to organize into a new matrix, and this matrix is called the ij minor of the matrix A. As I said, this creates a bit of a confusion with the notation. In the past, we have used the notation Aij to denote the element in position ij of the matrix. Now, these two sort of different uses of the notation are really not going to create any confusion in general. First of all, I will always tell you what the context is, and I will always specify if I'm talking about an element or I'm talking about a minor. Secondly, as I said, we're not going to deal with minors very much, so it's going to be a short-lived potential conflict. The second concept that we need to look at is the idea of a cofactor, which is related to that of a minor. If we look at this expression, -1 to the power I plus j times the determinant of Aij, of course in this situation I'm assuming that Aij is a square matrix, okay? This is called the ij cofactor of A. Okay. And you might wonder why that -1 to the I plus j. Well, again, that comes in with the Laplace expansion theorem. Okay, so let me give you just an example of what that means. Let's look back at our simple matrix A given in this way. So if I want to look at the cofactor -1 to the power 2 plus 3 A2 3, so that's the 2, 3 cofactor of the matrix. What I'm going to do is, first of all, I have to compute what -1 to the power 2 plus 3 is. Notice again that the exponent here is obtained as the sum of the two indices of the row and column. So what I'm going to do in this case is negative 1 to the power 5. Well, that's negative 1. Okay. And then it's time the determinant of the minor a to 3. So remember, that's the minor that we obtained by deleting the second row and the third column. Okay. That negative 1 to a certain power may look confusing at the beginning, but actually it's pretty easy to figure out whether that power is going to end up giving us a plus or a minus. Of course, it can't give us anything else except a plus or a minus, by realizing that the pluses and the minuses really lie in a checkerboard kind of pattern on the matrix. So we start from the top left, which is a plus, because it's negative 1 to the power 1 plus 1, which is 2. And then every time you move horizontally or vertically, that power of negative 1 changes from plus to minus. And if we move diagonally, then it's going to stay the same. Okay, so we can use this simple rule to figure out whether we're dealing with pluses or minuses. So we have now introduced minors and cofactors. It is time to see how they're used in the Laplace expansion theorem.